In the first game we looked at, the two players had dominant strategies, and those dominant strategies led to what was actually the socially optimal outcome. But a lot of times that's not the case, and one classic example of that is often called the prisoner's dilemma, so named for the idea that there are two prisoners who are separated, and one has an incentive to turn information on the other and get a lighter sentence. But if they both squeal on each other, then they both end up in a bad situation. In this case, we're going to do an example that's a little bit more economically related, where two farmers are trying to choose which pesticide to use. And in this case, we have two options. We have an integrated pest control, which the idea is that you introduce good bugs into the fields in order to eat the bad bugs, or you can use a chemical, Terminator. And the problem with Terminator is that if everybody uses it, then it pollutes the rivers, and you have to pay to clean it up, or you end up with health problems or something like that. And so then the question is, all right, well, what is the Nash equilibrium? And so again, we can go through our example and figure out what the Nash equilibrium is. So if Bala uses integrated pest control, then Anil is choosing between 3 and 4. So 3 if he uses integrated pest control, and 4 otherwise. 4 is bigger than 3, so we underline 4. If Bala uses Terminator, and Anil uses integrated pest control, he only gets 1. Otherwise, if you use Terminator, he gets 2, and 2 is better than 1. If Anil uses integrated pest control, then Bala is choosing between 3 and 4. 4 is better than 3, so we underline that. And if Anil uses Terminator, he's choosing between 1 and 2, and so he chooses 2. And so here we can see again that there is a dominant strategy, right? The dominant strategy in this case for both players is to use the chemical pesticide Terminator. But the problem is that we end up with a Nash equilibrium that is not socially optimal. And in this case, unlike the example from the previous video where we had two Nash equilibria, in this case the social optimum, which is both using integrated pest control, is not a Nash equilibrium. And so that's the problem with the prisoner's dilemma, is that we would like to be up here where both are using the integrated pest control, but because of the payoff structure, both have an incentive to use Terminator, and both would be punished if they unilaterally stopped using Terminator and went to integrated pest control, right? If Anil says, okay, I'm not going to use Terminator, I'll use IPC, well then he goes down to 1 and Bala goes up to 4, and Bala says, okay, that's great, thanks for doing that, but now has no incentive to go over to integrated pest control. So this is a problem that is fairly common, or at least commonly talked about, and we have to think about why we get there. And so for one issue is that players only care about their own payoffs, right? If I'm Bala, I don't care about Anil's payoffs, and if I'm Anil, I don't care about Bala's payoffs. And so one possibility to get away from the prisoner's dilemma is to introduce social preferences, and so we'll talk about that. The other problem is that we can't make anybody pay for the consequences of their actions, right? And so we could possibly make people pay for their decisions if we introduce repeated games where we're doing this over and over, or if we just have social norms, right? Where the village goes to Bala and says, Bala, you're using Terminator, you need to use IPC, and Bala says, oh yeah, okay, I don't want to be ostracized, so I'm going to use IPC. Or there could be pure punishment. And by pure punishment, we don't mean, going over to Bala and dragging him out of his house, but rather we can do something strategically that reduces Bala's payoffs for, 1 or 2 periods, and makes him not want to use Terminator, instead use integrated pest control. And finally, players cannot coordinate their actions beforehand, right? So it's possible that we could change the rules of the game, and we could say, hey, listen, we're going to use IPC. Now, there has to be some mechanism which can make people commit to that. And so it could be a law that we pass that says, okay, Terminator is banned. You can only use IPC. Or it could be some way that we sort of trick the market mechanism in order to make the payoffs clear, so that we get to the social optimum of both using IPC instead of both using Terminator. So one way that we can sort of figure out about preferences is doing experiments. And a lot of experimental economics sort of got started in the 1970s and has been going on since then, um, and has been taking place in labs. And the benefit of labs is that we can put people in a particular situation, tell them the payoffs, tell them what their possible strategies are, and let them, make their decisions. We can do it over and over. We can let them learn. We can replicate it. We can control for other variables. But the problem with lab experiments is that they are not usually very realistic, because usually the payoffs are low. It's not a real world environment. And so a lot of economists look at lab experiments and say, well, that's interesting, but what do we know about what people will actually do in the long run? And so some economists have been moving on to field experiments, and basically, going to especially developing countries, trying different experiments, different policies. They'll often have a control group and a treatment group, and seeing, how that policy affects actual decisions and payoffs. And those are more realistic, but they're obviously much, much harder and more expensive to do than lab experiments. So one way we can solve this problem of the prisoner's dilemma is to think about altruism. And so the idea of altruism is that I don't just care about my own payoff, I also care about other people's payoffs. And so in this case, we can think about that Anil's indifference curves may take into account both Anil's payoff, which is over here on the horizontal axis, but also Bala's payoff here on the vertical axis. Now, we don't necessarily need Anil to be perfectly altruistic and care equally about Bala and his own payoffs, but just a little bit altruistic. Then we can see that Anil may go from point A, where he maximizes his payoff at 10, but Bala gets 0, to a point B where uh, Anil gets 7 and Bala gets 3, right? That's on a higher indifference curve because I don't want to see Bala starve to death, and so I at least want to make sure Bala has enough. And so altruism is actually one way to solve the prisoner's dilemma, right? Because now, even though Terminator, right, this 0.22 is our Nash equilibrium when we only care about our own preferences, now it could be that IPC, this point here, 3,3, which was not a Nash equilibrium before, is now on a higher indifference curve, and so both Anil and Bala will actually choose IPC because they care about each other's payoffs, right? So remember before, if they had been here, one of them would have switched, or they would have both switched to Terminator in order to get the higher payoff of 4, right? But now, because they care about the other person's payoff, if they switch here to 4, the other person only gets 1. And so now that they switch to a lower indifference curve, and so this 0.33 II, where they're both using integrated pest control, is actually the new Nash equilibrium, simply because we care about each other's payoffs. And as I said, I think this is often a realistic situation in smaller groups where people know each other, rather than in a larger anonymous market setting where I might know that my payoff, or my action is going to affect the payoff of some random stranger. I don't know that random stranger, and so I may not be willing to switch my strategy based on their payoff.